Welcome to a sim code. Your like and subscribe show me that you want more great tutorials. Thank you for your support. Regularization is a technique used to reduce overfitting by adding a penalty term to the loss function. This penalty discourages the model from becoming too complex and helps in generalizing better on unseen data. L1 regularization, Lasso. L1 regularization adds the absolute values of the model weights to the loss function. This technique encourages sparsity, meaning that many of the weights may become zero. In other words, L1 regularization tends to produce models where some features are effectively ignored because their corresponding weights are reduced to zero. L2 regularization, RIG. L2 regularization adds the squared values of the model weights to the loss function. Unlike L1, L2 regularization does not drive weights to exactly zero, but it discourages large weights. L2 regularization results in smaller, more evenly distributed weights compared to L1 regularization. Importing NumPy for numerical operations. Let's start by defining the mean squared error, MSE, function. This function calculates the mean squared error, MSE, between the true target values and the predicted values. Arguments. Y_true, a NumPy array containing the true values, target values. Y_pred, a NumPy array containing the predicted values from our model. Returns. MSE, the calculated MSE value, which is a scalar representing the average squared difference between true and predicted values. Lower MSE indicates a better fit. So essentially, we're calculating how far our predictions are from the actual values on average. NP.mean computes the average of the squared errors. Return the MSE value to be used later in the gradient descent. Now, let's define the gradient descent function, which will use L1 or L2 regularization. This function applies gradient descent with L1 or L2 regularization to minimize the loss function. Arguments. X, a 2D NumPy array, matrix, of features, input data, where each row is a data point and each column is a feature. Y, a 1D NumPy array of true target values, labels, corresponding to the rows in X. Initial_weights, a 1D NumPy array of initial model weights, typically starting with zeros or random values. Learning underscore rate, a scalar value that controls the step size in each iteration of gradient descent. Epochs, the number of iterations to run gradient descent. The model updates weights this many times. Regularization, type of regularization. L1 for lasso, absolute value of weights, or L2 for ridge, squared weights. Lambda underscore reg, regularization strength, controls how much the penalty affects the model's loss function. Returns. Weights, a 1D numpy array of optimized weights after the gradient descent procedure. The idea here is to adjust the weights iteratively by calculating gradients, slopes, of the loss function. The regularization helps avoid overfitting by penalizing large weights. Convert initial underscore weights to a numpy array if not already. This is a good practice. Copying initial weights to modify them during training. Begin the gradient descent loop for the specified number of epochs. Make predictions based on the current weights. np.x weights calculates the linear model's prediction. Calculate the error, difference between predicted values and true target values. Calculate the gradient of the loss function with respect to weights. Mean of the gradient of MSE. Now, we add regularization to the gradient, either L1 or L2. For L2 regularization, ridge, we add squared weights penalty. For L1 regularization, lasso, we add absolute weights penalty. Update weights using the gradient and learning rate. Subtracting to minimize the loss, downhill on the gradient. Now let's calculate the total loss, including the regularization term. Ridge loss function. Lasso loss function. No regularization, just MSE. Optionally, print the loss and weights every 100 iterations to track the progress. This will print every 100 epochs. Return the optimized weights after all the updates. Example usage of our functions. Define example data, X. Input features, Y. Target output values. Each row in X represents a data point, and each column represents a feature. Example input matrix, 5 data points, 2 features. Corresponding target values, 1D array. Initialize the model weights to zeros, could also use random values. Number of weights equals the number of features, too. Set the hyperparameters for gradient descent. A smaller learning rate means smaller updates to weights. Number of iterations to run gradient descent. Regularization strength controls how much regularization we apply. Now, let's test both regularizations. First, we'll train using L2 regularization, rich. Then we'll train using L1 regularization, Lasso. Now run our code. That's it for today, folks. Please like, comment, and subscribe for more.